Hi everybody. Today we are on the 11th week and second session. Yesterday we have got EMF and torque equations, and finally we have developed equivalent circuit of the DC armature. And today I will remember you equivalent circuit of DC armature, DC machine, and then we will make some practical applications. Examples. Here are some solved problems in Turkish. I try to convert them into English right now on live. Let's start. First of all, let me remember you how was the equivalent circuit. First of all, let's remember symbol of machine. Let's say motor, DC, some figures representing brushes. That represents motor. Here's capital M. In fact, that is the representation of armature, terminals A1 and A2. In old literature, it is A and B. As you remember, to convert energy, you need some magnetic field. Here's the excitation coil. Let's say field 1 and field 2. That is the field coil terminals. That is the symbol of machine. That is the symbol of DC machine. Sometimes we say generator or dynamo. Let me draw dynamo. Again, that is the armature. Here would be permanent magnet. Permanent magnet is represented by such a figure. That is permanent magnet DC generator. Or sometimes we say dynamo. Dynamo is the nickname of DC generator. Again, terminals are the same, A1 and A2. And here is no terminal for field because there is no coil. Magnetic field comes from permanent magnets. That is the symbol of permanent magnet machine. I said machine. That system can be used as a motor or generator. The same configuration can operate in both style. In fact, but a little bit different design will help commutation. We will talk later. Only brushes are slightly in a different angle. Let's say brushes are here in generator operation, but if you change angle of brushes, let me say that is the commutator, brushes like this, here would be smaller arc, so commutation will be easier. There will be much more smaller arc, so we generally change position of brushes in different applications, in motor or generator applications, but without making any adjustment, the same system can operate it as a motor or generator. It doesn't matter. If you make proper adjustment in brushes position, so there will be a little bit less arc will be observed, so life cycle of the brushes will be increased by making proper adjustment in position of brushes. It's another topic we will talk later, commutation and armature reaction. Today I will remember you the equivalent circuit. Okay, here was the armature. Here is the armature. Let's say A1 and A2. There are, let me write it down here, DC armature, and you remember what we talk about. That is a DC armature. DC rotor. Armature is the place where energy conversion occurs or where the electromotive force is induced. That is the system part. Rotor induces electromotive force, makes energy conversion. So we call rotor as armature. That system contains armature windings. Here you see some commutator segments, and there would be some brushes touching to commutator segments as you see here. Okay. Now, our aim is to make an equivalent circuit for the armature. As you remember, we have developed EMF equation. Here is EMF. EMF was Ka times flux times angular speed of the shaft. That EMF is induced across brushes, and there was a resistance of copper winding in rotor or armature. And again, here is an inductance of armature, but in steady state we neglect inductance because there is no effect due to inductance. We only use EMF and armature winding resistance. That is the terminal A1 and A2. Between terminals there is an equivalent circuit. There is an EMF. It is a dependent voltage source, dependent magnetic flux, and speed. In case there is no speed, let's say machine is in standstill position, there will be no EMF. If there is no magnetic field, there will be no EMF. Those two parameters are essential. Without there is no movement, mechanical energy, or there is no magnetic flux, there would be no electrical output induced. That is the equivalent circuit. As you see, here's a field circuit. Let me just give some idea how can we generate magnetic field. Let's say that is a motor, and let's say here is a field coil having F1 and F2 terminals, and here on A1 and A2, and let's connect that machine to a DC supply. Here's a DC terminal voltage plus and minus we apply. So machine draws a load current, and then Houston, to convert energy you need magnetic field. Here's a field coil, so you should supply some electric power to field coil. Let's say that is field current, that is armature current, and here field coil, field winding is connected shunt to armature. So that motor is called as shunt motor. That is just a connection. Here is the mechanical output, shaft, and again let's say here is a motor again. It would be a generator, of course, and here is maybe A1 and A2 terminals. Here is a field coil. Let's say that is a different design. Labels are S1 and S2. I will talk a little bit later. And then let's connect that device to a DC network. Houston, there's a different configuration. Yes. We apply terminal voltage. Machine draws load current. Here's the armature current. Houston, here is the field current. Beep beep. All those currents are equal. Yes. Because we have connected field coil Series. Beep beep. Is it always possible? No. This guy has a special design. Field coil can carry armature coil current. Here's the armature is the place energy conversion occurs. So this current is generally large. Let's say that is 100 amps. Let's say that is 1 amp. Current is large here in armature. So this coil is directly connected to voltage, as you see, having high resistance. Let me say our shunt is very high resistance to draw smaller current because it consumes some power, as you see. And then this device can carry, let's say, 100 amps armature current, energy converting device. But this field current must be equal to this one. So this coil is very large in thickness. Let me say there's a pole. There is an electromagnet on pole. Let's say that is thinner coil, larger number of turns. That is shunt because it needs high resistance to draw smaller field current. But let's talk about serial design. The same pole, the same electromagnet, in this case has a larger coil, larger in diameter coil. As you see, copper coils are very larger, carrying too much current, carrying high current of armature to make high energy conversion. So to eliminate losses, serial field coil must have a resistance as low as possible, as small as possible. Now here we prefer as high as possible. Now you should make a proper design to have as small as possible. That is a different machine. The terminal labels are field 1 and field 2, but here terminal labels are, S1 and S2, serial 1, serial 2. As you understand so far, machine will have different connection types. So applied Kirchhoff voltage law and current laws will result in different results. Related with the connection diagram, equivalent circuit will be a bit different. For example, for this you can make an equivalent circuit. Here is, let's say, VT, a voltage source, plus and minus, and then here is a resistance of field or shunt field winding. In fact, there is inductance of this coil, but we only deal with steady state operation of machines, so there is no need to use inductance. There is no effect in steady state. And here is the armature having armature resistance and armature EMF plus and minus. Let's show current direction. This is motor drawing some load current. Here's the field current or shunt field current. Here is the armature current. That is the equivalent circuit. First of all, you should imagine the connection diagram, and then you should draw equivalent circuit, and then we will apply Kirchhoff's voltage law and Kirchhoff's current law to get results. Okay, let's do equivalent circuit of this serial one. Here's the terminal power supply voltage. Let me represent it by a simple battery. That is the power source. That is terminal voltage of battery or power source. Here is a serial resistance of field coil, series field coil I have shown. And here is armature winding resistance, and here is the EMF. That is the equivalent circuit of below serial connected DC motor. Here is the current I load or terminal current drawn from the power source. Here's the field current or serial field current. Here's the armature current. All triple current parameters are equal in serial machine. So machine has got a different design to carry high armature current via field coil. That was just some information to remember you equivalent circuit and some connection types and how equivalent circuit will be implemented in different connections. And I have summarized here 2 different connections for motor operation. In fact, there is one more connection diagram which is compound motor. I will talk later. And there are also some generator connections. The same connection, for example, this guy. Let me draw just shunt generator. Here is the armature. The same figure comes dynamo or generator. Here are the terminals A1 and A2 and Houston. Here's the shunt coil F1 and F2 labels. Sometimes we show like this. Both are correct. That is the symbol of DC machine. They are together. But in this case, I operate machine as dynamo. So this guy driven from the shaft, we apply some mechanical input, ladies and gentlemen, and then that mechanical input converted into electric power in armature. It induces electromotive force, as you remember, and then you deliver it to the terminal. Here is the terminal voltage. Here is the load, electrical load supplied from the dynamo or generator. Houston, there is no magnetic field yet. Yes, magnetic circuit, field circuit must be connected properly. Since I have mentioned it was shunt, so field coil parallelly connected to or shunt connected to armature. That is the shunt generator. It induces electromotive force. It supplies the load, that is the load current, and it supplies itself, self-excitation. There are some requirements we will talk later. It is not it is easy, but you need some ceremony before self-excitation. So let's say it is ready for self-excitation. When you draw a machine at a speed, when you apply some mechanical input power, here is an electromotive force. That electromotive force, here are positive and negative polarities. Supply external system, which is one is field circuit, the other is load circuit. As you see, current directions has changed in different operations. That was motor operation. Electric energy applied from the terminal and converted here in this armature into mechanical power. And here mechanical energy applied, converted into electric power here in armature. That induced electric power will supply itself and load. So, first of all, you should know the connection of the circuit, and then you should imagine how can you make an equivalent circuit. Let me show you the equivalent circuit. Here is the EMF, plus and minus, dependent voltage source. Here is the equation. And then inside the armature there is armature resistance of copper windings. As you see, here are copper windings. That is the resistance of copper windings. And then Houston, here's the shunt field, let's say shunt resistance. I have not deal with inductances because they make no effect in steady state. And here's the load, electrical load. Again, in DC you can simply substitute load by a simple resistance, let's say R load. And then that's it. That is the load current. That is the terminal voltage between terminals on the across the load. That is the terminal voltage or network voltage you generate in the armature. In fact, you generate here, and then there is a voltage drop across the load. That is the VT, terminal voltage. And here's the load current. Let me say IL. Here's the field current of shunt field current. Let's say RFSH. And that is the armature current. As you see, armature induced electromotive force that power supply itself, self-excitation, and it also supplies load. We will talk deeply later, but I just want to inform you how we use equivalent circuit. Okay, to practice, let's solve an easy problem. Here is our website, you know, there's a reference file. I have downloaded this file, and let's talk about the sixth question.